Hello, and welcome to episode 2 of Complex Conversations. I am your host, Luke Bates, and today I'm joined with Luke Evans and Matthew Hollis. We will be discussing some of the less simple concepts surrounding the Mandelbrot sets. Proving the triangle inequality, proving the reverse triangle inequality, and a proof by induction. So, let's start with the triangle inequality. Matthew.
So, the triangle inequality is where you have one complex number, z1, and another complex number, z2. So if you take the modulus of z1 and add on the modulus of z2, that is greater than or equal to the modulus of z1 plus z2. And this can be seen on an Argand diagram, as discussed last episode, where Luke will explain how this can prove this statement.
Thank you, Matthew. So on this Venn diagram, we've plotted the modulus of z1 at a point A and the modulus of z2 at a point B. We've also plotted point C as the modulus of z1 plus z2. Now, you can make a parallelogram out of this, as AC will be equal to OB and BC will be equal to OA. This forms two identical triangles, with the longest side being the modulus of z1 plus z2, and the other two sides being the modulus of z1 and the modulus of z2, respectively.
As two sides of a triangle, when summed together, is always greater than or equal to the other side of that triangle, we can prove the reverse triangle inequality, as shown right there. Now, onto the application of this, proving the reverse triangle inequality.
Cool. So, with the reverse triangle inequality, you can take the fact that the triangle inequality is true and let z1 equal negative b, let z2 equal a plus b, where a and b are subsets of the complex numbers. Because of the triangle inequality, you can write the modulus of negative b plus the modulus of a plus b is greater than or equal to the modulus of a plus b minus b. Now, simplifying this down, you will get the modulus of negative b plus the modulus of a plus b is greater than or equal to the modulus of a. Since the modulus of negative b is equal to the modulus of b, you can rewrite this as the modulus of a plus b is greater than or equal to the modulus of a minus the modulus of b, which could also be represented in this form as a and b are both complex numbers.
Which brings us on to our final proof to look at, a proof by induction. Well, firstly, Matthew, what is a proof by induction?
So, a proof by induction is where that if you prove for a certain base case, which is of a natural number, that a claim is true, and then you assume that an arbitrary previous claim is true, and that the following claim, assuming that previous claim is true, is also true when using that previous claim, that this means that all that you claim that is true. This means that all of these claims, including from the base case and up, will all be true.
So can you do a proof by induction? The claim being summing the terms in the Fibonacci sequence, FR is R2 Fn is equal to Fn plus 2 minus 1.
So firstly, we have F1 and F2, so the first two values of the Fibonacci sequence, which are both 1. To get the third term, we can add these together, which gets us 2. So Fn, so the first Fn being the first term, we want to say it's 1 because that's the first term. So we have 2 from the third term minus the 1, and then that just gets a 1. So therefore, for n being 1, the claim is true.
Ooh. So for the inductive step, you will assume that the claim is true for n equals k. So you can write this as the sum of the first k Fibonacci terms is equal to the f of k plus 2 minus 1. Now, because of assuming this inductive step, you now let n equal k plus 1. You can write this as the sum of the k plus for 1 Fibonacci terms is equal to the sum of the first k Fibonacci terms plus the k plus 1 Fibonacci term. Now, because of your inductive step, you can rewrite that sum as f of k plus 2 minus 1 plus f of k plus 1. Now, because of the Fibonacci sequence being the previous two terms added together to form the next term, f of k plus 2 plus f of k plus 1 is equal to f of k plus 3. And you remember the negative 1, so f of k plus 3 take away 1, which is as the claim requires.
And then therefore, as stated as above, we meet the base case scenario, as well as assuming the previous term is true, the next term is true scenario also, both of those. Therefore, we can say that via induction, that this claim is true for all values above 1, so any natural number.
Thank you, Matthew, and thank you, Luke. And thank you for listening to this episode of Complex Conversations. We're talking about the Mandelbrot set next week, how to derive it, and what it looks like. See you there.